Mainly because the elemental halogens, particularly bromine and chlorine, those two, they're more dangerous and more difficult to handle, not as safe. You used bromine in organic 1. With me, it was a 10% solution. 90% of it was solvent. Imagine using pure bromine. It's a very volatile liquid. You've got to be very careful using bromine. Chlorine, Cl2 is a gas. Be very careful with it. Okay, the reagents you use generated electrical halogen by some unique mechanism or other means. All right, just discussed a little bit in that pre-lab. Textbook though is to use bromine or chlorine, and so that's sort of what we're focused on. And I told you could do mechanism in your report just using that. Now what about iodine? With iodine, you cannot use a Lewis acid. Lewis acid complexation doesn't work. You actually have to form I+. Single atom, I+. And to go from iodine to I+, you need an oxidant. Okay? We didn't use an oxidant with bromination or fluorination. We just used Lewis acid. Okay, to polarize the halogen. All right, you need an oxidant. Common oxidants to do this, actually copper chloride, copper being oxidation state of 2+. Copper 2+ is an oxidant, mild oxidant. Iodine gets oxidized, the copper gets reduced down to copper 1. Hydrogen peroxide, a non-metal oxidant. Periodic acid. So these are non-metal oxidants. You sometimes can even use nitric acid as an oxidant. The problem with nitric acid is it may actually nitrate your ring, which you did in lab last week, and we'll see that on the next page. You got to be careful about that because you might get a reaction you don't want. You have to do it just right. So, line reaction can be reacting this with iodine. We're talking about elemental iodine, but an oxidant like copper chloride, and we can get a product here. I'm not going to go into how this leads to, but this is going to generate I+. All right? And then once you generate I+, you can just do your mechanism. On the front page, we used E+ as a generic electrophile. We'll just replace the E with I, and you've got your mechanism. I+. All right? Sigma complex, resonance delocalized sigma complex. And then the second step, the second fast step, removing the proton to restore the aromaticity. Put the pi bond back in. It's the same mechanism. Just need to understand generating the electrophile. All right. I'm not going to show the fate of everything. It's not completely balanced, but this is how you often iodinate rings. And those that did iodination of sulfonilamide, you generated I+ from a combination of iodide. You didn't start with iodine, you started with iodide. This has to first go to I2, and then you get to I+. So this is -1, this is +1, but this is elemental. So it required 2 oxidations, because you started with potassium or sodium iodide. Who did iodination? Sodium iodide. That supplied this, but you had to oxidize it. What was the other reagent? Wasn't it KIO? It was actually O3. It wasn't O4. You could use O3. It wasn't the acid, it was the anion. But didn't you also use some acid in this reaction?
H2SO.
Yeah, that's going to protonate this and make it like HiO3. But it's an oxidant. It happened to have iodine here, but it could have been other oxidants. This oxidized this all the way here. And it may be a little bit unclear because in some cases I2 can react. Certainly it turned dark. It's a little bit unclear. We haven't talked about it yet, but activating groups. If you have an activating group, it may be possible to just have a reaction with I2. But textbook is to oxidize to I+. What about fluorine? By the way, iodine tends to be less reactive than bromine chlorine. That's why you have to actually get I+. And just a complex doesn't work because iodine is just not inherently as electrophilic, not as reactive towards nucleophiles. Fluorine, on the other hand, is just the opposite. F2 is so reactive that reactions tend to be dangerous. Reaction F2 can be very explosive. No Lewis acid required. No oxidant required. F2, very reactive. Why? Because the FF bond tends to be very weak. And if you're trying to fluorinate a carbon, like in the benzene ring, you're making a very strong CF bond. And so your thermodynamics are very favorable. It's very thermodynamically favorable, very exothermic reaction. Very exothermic reactions are often quite fast. They don't have to be, but this one is. It tends to be very explosive, and the fluorine chemistry field is often a number of accidents known or reported. Used to be a chemist at Clemson who did fluorine chemistry, and he was missing half of an arm and 3 fingers because when he was in graduate school, there was an explosion. Okay. I happened to have a chance to have lunch with him a few years ago. Okay. We will see a diazonium reaction. This is a much better way to put a fluorine on a ring, or to have a fluorinated product. Fluorinated aromatic. We'll see this later. Diazonium reaction. Now, just a miscellaneous comment, there are some unique reagents called NF reagents where the fluorine is bound to a positive nitrogen and you can attack the F and kick off the positive nitrogen. I've used these a good bit. These tend to be very stable solids, and so they can be weighed out and used much more safely instead of an explosive gas, which fluorine is. There's a little blurb on outside my door about the isolation of fluorine. Back in the 1890s or so, when it was first isolated, and it said that some of it fell on the wood floor, and the wood floor immediately caught fire. Because what is wood? Carbon. It's an organic compound. Okay. And fluorine will react with just about any organic compound very exothermically. And so it just falls and ignites the floor. That's pretty reactive. Okay. It also talks about how it was distilled or condensed. It's a gas, but you can condense it into a liquid. And it said it would occasionally it would detonate. And then it said that eventually so much built up that the detonation was so strong that it exploded the flask or something. So there's a lot of interesting writing about isolation of F2. Imagine reacting it with something. Okay, we'll see diazonium later. B, so halogenation. What about nitration? Very common reaction with aromatics. Here the electrophile is the nitronium ion, NO2+. This is the electrophile. This is what the ring attacks. Lewis structure for nitronium ion here. Most commonly, this comes from nitric acid and an H+ catalyst. We can go from benzene to nitrobenzene. Now we're doing nomenclature. Pretty good? Pretty straightforward? Nitrobenzene itself is a little toxic. It used to be used in shoe polish. You know the reminiscent smell of old shoe polish? The nitrobenzene. It's actually a fairly toxic compound, though. That's one historical use of it. It can be used in some solvent properties. Of course, benzene's carcinogenic. Nitrobenzene probably is too. Occasionally, you might see it as a solvent because of certain reasons. It's kind of nasty, smelly, very high boiling, hard to get rid of. The nitro group has Lewis structure here, coming off the ring. Okay, it's two charges. Net neutral. It's a neutral group. There's no way to draw it without two charges, though. All right. Of course, this anion is delocalized onto this oxygen, and so which NO bond is longer, the one going up or over here? They're the same. They're the same. This is really a hybrid here. Yeah, this is plus, partial minus, partial minus. That's the truer representation of a nitro group. You can see it. You know, the two NO bonds are the same, exact same bond order. You should be able to draw resonance structure there. All right? It's very symmetrical. It's the old idea of resonance. There's your resonance hybrid. There's your nitro group. Very often we just say NO2. Okay? It's a very common group. It's analogous to a carboxylic acid. I mean, if this is carbon, and we had the same electron makeup, isoelectronic, this would be minus. This carbon would be neutral. And that's a carboxylate. And you'd have to have like a sodium or something sitting with it. But if we change this to nitrogen, well, that's the nitro group. But the nitrogen is now positive. Because nitrogen doesn't make 4 bonds like carbon. And since it's positive, it can balance this O minus, and you don't need anything else. And it can just be a complete neutral group like that. Okay. Really, we just need to figure out how do we make our electrophile. Because once we make our electrophile, well, then the ring just attacks. And it does attack the nitrogen. We can show it attacking that. How do we get that? Well, nitric acid. Nitric acid has Lewis structure of it's OH. This is typical structure of nitric acid. HNO3. How do we get to the nitronium? What do we need to lose?
OH group.
OH. Seems like OH needs to leave. Everybody agree? Mm-hmm. In general, how do you make OH? Is OH a good leaving group? Let's talk SN2 type leaving group. Is it OH a good leaving group? How do you make it a better leaving group?
Protonated.
Protonated. H+ catalyst. What do you think it's for?
Protonated.
Protonated. And that's going to give... Well, hold on here. This is quite odd. We just protonated a strong acid. That don't make sense, does it? Protonated acid? What is this, like Twilight Zone stuff? No, that's what we're doing. I just protonated nitric acid. So someone says, is nitric acid an acid or a base? You say, well, it's usually an acid, but today in class we actually saw it act as a base. Imagine that. This, how can we get here? This needs to leave. Well, you could do 2 arrows or 1. I'd rather do 2, because if this just left, it's going to make that nitrogen what charge?
2 positive.
2 positive. I'd probably avoid that. But we can sort of do it this way, and I said it before, we'll say it a million times going forward. Anytime you can make a pi bond and kick off the leaving group, that's typically fast and easy. Look what we can do. These electrons, pretty electron rich, move them in and kick this off. What does that electron movement do?
The nitronium ion plus
It
one.
gives nitronium. The nitrogen's still positive. Plus what? What did we kick off?
Water.
Yes, there we go. This will take place. What type of acid is typically common here? What would you use? Strong acid. Anytime we use H plus catalyst, that's strong acid. What's the common here?
HCl.
Again?
Sulfuric acid.
Sulfuric acid is very common. Yes. Or nitric acid could be used. Well, we are using nitric acid. Guess what? Nitric acid can protonate itself. Weird, right? Isn't nitric acid a strong acid? Yeah. This is strong acid. What are examples of strong acid? You learned in the Gen Chem. Sulfuric. Nitric acid is a strong acid. Nitric acid can protonate itself. So you don't actually have to have sulfuric. You can just use nitric acid. Now sulfuric tends to be a stronger acid than nitric acid. This reaction is faster with sulfuric acid. But nitric acid is strong enough to protonate itself. If you use sulfuric acid, you got to be even more careful because it can nitrate faster and faster, and then you get dinitro, trinitro, TNT. Okay. We would never have used sulfuric acid this last week in lab. Too reactive with nitric acid for me. We would have had to have been, sitting on a one-legged stool. All right, very careful. But textbook, nitric sulfuric. But nitric acid can protonate itself. Okay, get your nitronium ion. Once you get it, then the ring will attack it. Very reactive. Very reactive. And so we got our ring here. And these electrons, either way you go, it doesn't matter where you leave cation, right? These electrons can pull away and attack here. Nitrogen can only have 4 bonds. You can't put 5 bonds around nitrogen. Forget about charge. We attack here, we move one of the pi bonds away. Doesn't matter. And that gives what? I'm sort of hinging down here. So I hinge down to make bond to that nitrogen. We've got double bond to an oxygen and just single bond to oxygen. But now this oxygen should have how many lone pairs? 3, and that's a minus charge. But the nitrogen is still positive, even though it was attacked. Because we move electrons over. It's still positive. There's an H here, there's a plus here. Here's our sigma complex, just like previous mechanisms. Resonance stabilized. And then what's the next step? How do we get nitrobenzene? Right? This is our slow rate determining step, making the sigma complex, ring attacking electrophile. Something takes the H. Okay? For example, back over here, if we use sulfuric acid, we've got this. This can take the H. These electrons move in here to put pi bond back in. And that gives this, and we're reforming sulfuric acid, which if we're going to say that was the catalyst. Or you can reform nitric acid if you want to say that's the catalyst. But the original H is regenerated right here. That H then turning around and going back as the acid H. Same old mechanism. What is the electrophile? Here it's the nitronium ion. Okay, while we're on the nitro group, a common reaction of nitro groups is to reduce them to amino groups. And that is a reduction. Because we're adding H's to the nitrogen. That's one way to see a reduction. We're also decreasing the number of bonds to a more electronegative atom. This has, depending on resonance, I mean, it's bonded to 2 electronegative atoms. Now it's bonded to none. You should see that that's a reduction. And a common way to make NH2 groups, amino groups, is from nitro groups. Very common. But it's most common on aromatic rings. Some side chemistry, some other chemistry can take place with sort of aliphatic compounds, and nitro groups are just not as common. Very common on aromatic rings. This is often done with some type of active metal. Your metals tend to be reducing agents because these guys don't mind becoming positive. They don't mind becoming oxidized. And if a zinc becomes positive, that means it's losing electrons. It's being oxidized. Well, then something must be reduced. Well, the nitro group's being reduced. Some type of active metal with acid catalyst. But it's not actually a catalyst. Because you actually need it. The H's actually become part of the molecule then. Okay. So someone may say catalyst, but it's actually, you need stoichiometric amount. All right. I mean, because that's where the H's come from. The acid, the H+. And you'll actually be doing this in lab this week. You have choice of 2 different metals to use. And 2 different conditions. Your choice. Okay? I think the choices are either zinc or tin. Iron did not work as well. Sometimes iron works well, sometimes it doesn't. You can also do this reaction. Hold on. With a metal, it's often called a dissolving metal reduction. For example, the iron, it starts out iron and acid, and the iron becomes ion, and it's now soluble. The metal ions become soluble. But at the outset, it was metal, it was iron metal. And your metals are not soluble in anything. So it starts out, you just see this metal suspension, but as it reacts, it sort of all dissolves. And so it's often generally called a dissolving metal reduction. The metal dissolved, and you got a reduction. By the way, you probably learned in Gen Chem that a lot of metals react with acid to generate hydrogen. Now, hydrogen actually can be used for this transformation. You can do hydrogen and like a transition metal. A lot like you're reducing an alkene or an alkyne. The same conditions will reduce a nitro group to an amino group. All right? And we're not going to be looking at that mechanism. Okay? So that's just a reaction for your toolbox. How to reduce nitro groups, dissolving metal reduction, or hydrogenation. And I've reduced a lot of nitro groups, many times this way, but also hydrogenation. Tends to be a wonderfully nice, clean reaction. But we'll be using a metal in lab. So that's the most common way to make like anilines. It's very hard to put the amino group on directly. It's much more easier and less common to first nitrate, then reduce. So a two-step route to amino compounds. Next, sulfonation. You can put this sulfonic acid, okay? Sulfonic acid, that's the group. When it's on benzene, this compound is called benzene sulfonic acid. By the way, if you put a methyl on here, what's the name of this compound? Tosyl acid. What if this was, instead of an OH out here, what if this was chlorine connected there? Tosyl chloride. Yes. Tosyl acid, TSOH. I mean, if this here, don't write this down, but if that was binding to an OH, what would that molecule be? Sulfuric acid. This is just where the OH of sulfuric acid is replaced with some organic group. Okay? It's still a very strong acid here. It's no longer diprotic, monoprotic, but it's organic now. And this can be dry. That's one thing about it. This is a dry acid. Where sulfuric acid is not dry. Sulfuric acid is always aqueous. And there may be some cases where you want your strong acid to be dry, because you don't want any water. And in that case, tosyl acid is a common good choice. All right? A dry strong acid. All right? So, how do you make benzene sulfonic acids? SO3, sulfur trioxide, and sulfuric acid catalyst. SO3, it's kind of a little bit uncommon. The only time we'll ever see that. SO3, you can draw a Lewis structure. Actually, you can just do that. How many valence electrons? Sulfur, oxygen, 6. That's 6 times 4. 24? Mm-hmm. Okay. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. There you go, 24 valence electrons. Any charges there? No. Oxygen looks good. What's charge of sulfur here?
Neutral.
It is neutral. Everything's neutral there. There you go. There's your little structure of SO3. How many electrons are around sulfur, though? In terms of an octet count. Yes, it's 6. That's why it's neutral. But 12. I thought you could only have 8. Sulfur can expand its octet. That's an expanded octet for sulfur. Okay? These oxygens are very electronegative compared to sulfur, more electronegative. We can move electrons back and get an alternative Lewis structure. Like that. But these electrons are going to be attracted here. Instead of doing that, let's bring in the H plus is known to help this. You can protonate here. It's protonated SO3. Protonate one of the oxygens. Now this oxygen is going to be much more eager to pull. Now this pulls even more, and we can get to basically I show two different ways. Electronegativity pulling. And we can say, hey, this sulfur has some positive nature. But how much is this oxygen going to pull? Because positive nature, as it builds up, why would this separate? Charge separation is not great. We got electronegativity, but these electrons are going to want to go kind of back. So there's an in-between. Yeah, it's a hybrid. But if we protonate the oxygen, now it's going to want to pull. We made it mad. It's like, okay, sulfur, you got to give me your electrons. And so now we can get more of a positive on the sulfur. Because oxygen's like, I'm just taking them sulfur. I'm going to leave you plus because I don't want to be plus. Basically, protonation of the SO3 gives us more positive on the sulfur. Now this exists here. Now the ring will attack the sulfur. And when you attack the sulfur, you don't have to move any electrons away from the sulfur, like we did with the nitro group. And when we attack the sulfur, the ring is bonded to a sulfur, 2 double bond O's, OH. The ring is bonded to a sulfur, 2 double bonds, OH. You just attack the sulfur and everything's done out there. Of course, that's going to leave a sigma complex, and you're going to have to remove proton to go back to neutral. So whatever gave up the acid can take the proton back. So, in the end, what is the electrophile? It's the protonated SO3, which the sulfur becomes electrophilic. Electrophilic enough to be attacked by your aromatic system. Sulfonic acids. Not as common as nitration or halogenation, but still worthy of knowing. Sulfonation is actually reversible. You know, in theory, just about any reaction is reversible. I mean, we can start it, it'll come apart. But sulfonic acids can be removed fairly straightforward. that's routinely removed. It's just the opposite. You go back to your non-sulfonated and you generate SO3. The mechanism is just the reverse. And it's done by H plus catalyst. You can provide mechanism on your own. But what replaces the SO3 group? What is there now? Just an H. You got to get the benzene ring of your starting material to attack an H. Well, it attacks H plus. Over here, the benzene ring attacked the cation. It's S plus. Well, here's the same thing. The benzene ring attacks a cation. It's just H plus. You can try that on your own. It's just move your arrows to get your electrons to go where you need, break the bond you need, and form SO3, like I said is formed. Good practice for you to sit down and see what's going on there. Show a mechanism for that. Thus, sometimes the sulfonic acid can be used as a protecting group. Protecting group. We may mention that later. What a protecting group is. Anybody heard of protecting groups before? What have you protected?
Oh, I mean, I was in the book for alcohols, there's section 2.
Why did the alcohol needed to be protected?
Yes.
For what? Why? What?
I don't remember that.
Maybe to make a Grignard somewhere else in the molecule?
No.
Because you can't make a Grignard if you got an OH, so you can protect the OH,
Right.
mask it, or convert it to something else. Then do your Grignard, and then demask it, and come back, regenerate the OH. Yeah, it's, a lot of reasons where, okay, protecting groups, big deal in organic chemistry. Synthesis. Sometimes you have incompatibilities. And so you have to kind of protect some group where you can do chemistry over here, and then after you do your chemistry, then you deprotect. We mentioned amino groups. Here's a drug that has an amino group on an aromatic ring. I bet you a stake dinner that this was, when this molecule was generated, this was probably a nitro group at some point, and then they ultimately reduced the nitro group to the amino group. Okay. Substitution effects. We come back over here. We've looked at halogenation. We looked at nitration. We know nitration, we can go to amino. We'll do a reaction with the amino called a diazonium. That's coming later. Sulfonation we just looked at. We want to now look at putting on carbon groups. Either a plain carbon like an alkyl, or here an acyl. Carbonyl groups often called acyl groups. Okay? That's sort of a generic for a carbonyl substituent. Well, both of them are carbons. Carbon coming off the ring, generic carbon coming off the ring. But before we do that, though, we need to take a little detour. Okay? We need to take a little we need to travel to the land of substituent effects. Okay. We know we have benzene and we brominate it. You're just going to get bromobenzene. Where's the bromine going to go? Doesn't matter. All 6 carbons are the same if you're just dealing with benzene. But what if we are trying to brominate toluene? We can brominate it, or nitrate toluene. Where's the nitro group going to go? Is it going to go, what's the position next door to the methyl group?
Ortho.
Is it going to go ortho? Because if it went here, that would be different than, if it went here, that would be
Meta.
meta. Or it could go para. Once you have one substituent, the other locations are no longer all equivalent. What we have to ask is, what is the effect of the methyl? And that is a substituent effect. We have to understand substituent effects. And there's two things to look at with substituents effects. What I described was directing. How is this going to direct the incoming group? And that's actually number two. The first thing we're going to look at is, how does the methyl make the ring more or less reactive? Is toluene more reactive towards nitration or less reactive towards nitration than benzene?
More.
And that's called an activation-deactivation effect. Okay? Let's first look at that. All right. Two types of groups net. Electron donating groups. The net effect can be this can donate, can be an electron donator, or the group can be an electron withdrawer. Electron withdrawing group net. If the group is a net donator, the ring will be more reactive than benzene. Because the ring, what type of charge occurs in the ring in your mechanism? Sigma complex. What's the charge we generate in the ring? Positive. How do you stabilize positive charges? Do you donate electrons towards them or pull away?
Donate.
Donate. Donation is going to stabilize the positive charge and make it easier to form. And thus it's going to be more reactive. But if you're generating a positive charge and this is withdrawing, that's not good. That's not going to stabilize it. It's going to make it worse. It's going to make it more difficult to form that positive charge. More difficult to form, it's going to be less reactive than benzene. So we have to figure out how groups act. Net though. Because sometimes a certain group can act both ways. And we have to say, well, what's the net effect? Okay? Well, transition state. So what I just described here is shown here with the reaction coordinate diagram. This being benzene, right? We have some transition state leading to our sigma complex, resonance stabilized cation. This is our intermediate for EAS. If the group out here is a net donator, it's going to stabilize this intermediate and make this lower. Well, if that's lower, the transition state leading to it is typically going to be lower. This is going to be an easier reaction with the donating group. On the other hand, if it's a withdrawing group, that's going to hurt the cation. It's going to make the energy higher. Thus, the transition state leading to this is generally going to be higher. And that's going to be a more difficult reaction. So that's the same thing I described earlier. Just there we're looking at reaction coordinate diagram. Okay, I'll go through various types of substituents. Most books categorize these a little bit slightly different. I think I'm going to end up with 4 groups, where many books may only do 3, because I separate 2 groups a little bit. Okay, so you may see a little bit of difference. Group 1. Finishing up here. Certainly please be looking ahead at these groups. Group 1, I'm going to call strong activators or strong donators. This means the same thing. Because a donator is going to lead to a more activated ring. Okay? So strong activators. This is going to be atoms with a lone pair other than halogen. Not halogen. But like oxygen or nitrogen. And we'll basically pick up here next time. But an example of this would be right here. What's bonded to the ring? An atom with a lone pair. But it's not a halogen. So this right here is what I'm saying is a group 1. Okay? We'll explain everything and we'll move on to groups 1 through 4. 1 and 2 are going to be activators. 3 and 4 are going to be deactivators. With benzene sitting right between 1 and 2. Benzene being sort of the relative starting point. Please be looking ahead at these details here. Okay? And what type of group would the methyl be? It wouldn't be group 1 because it's not an atom with a lone pair. That carbon doesn't have a lone pair. It's not group 1. Okay? That's what we're doing here. Assessing different groups. Have a good day, guys.
Can you still use this as group criteria